friends, welcome to my latest video which focuses on phase changes and calorimetry. The effect of climate change is real. It's the dry season here in the Philippines and everybody is feeling the onslaught of this dry spell. Drinking enough water can beat the scorching heat and keeps you hydrated. The water that evaporates from one's body through perspiration has to be replenished. So find out more about this natural cooling mechanism among many warm-blooded animals, including humans. Stick around, watch, and learn. Our question number one. Evaporation of sweat is an important mechanism for temperature control in some warm-blooded animals. What mass of water must evaporate from the skin of a 70.0 kilogram man to cool his body 1.00 Celsius degree? The heat of vaporization of water at body temperature, which is 37 degrees Celsius, is 2.42 times 10 to the 6 joules per kilogram, and the specific heat of a typical human body is 3,480 joules per kilogram Kelvin. Question letter B. What volume of water must the man drink to replenish the evaporated water? Compare it to the volume of a soft drink can, which is 335 centimeter cube. Our solution to this question. We will first determine the amount of heat liberated by the man to cool his body by 1.00 Celsius degree. We will let Q sub 1 be that amount of heat, and that is determined by this formula. Q1 is equal to mass of the man multiplied by his specific heat multiplied by his change in temperature delta T. We will also determine Q sub 2, which is the amount of heat absorbed by the water to evaporate. Alright, so moving on with our solution, we say that Q1 is the amount of heat that the body has to release or liberate in order for him to drop his temperature by 1.00 Celsius degree. How can this be made possible? Alright, so the natural way of releasing heat from our body is by perspiring, or through the natural process of perspiration. So when the perspiration or the sweat in our body evaporates, it leaves behind on the skin a cooling effect. All right? So if Q1 represents the amount of heat that the human body should release, all right, when he is going to perspire, that amount of heat will be absorbed by the sweat or the perspiration in order for the water or the sweat to vaporize. In other words, to turn from liquid to water vapor, right? And that is represented by Q2, which is determined by multiplying the amount of sweat or the amount of water our target variable is that amount of sweat or the amount of water, all right, to be multiplied by a constant known as the heat of vaporization of water from the body at normal body temperature, right? So we have to isolate first this mass of the water that you have to drink in order to replenish, okay, the amount of water, right, that evaporates from the body. The fact that these two Q's, Q1 is equal to Q2, then we can just isolate NW, then equate it to this amount of heat Q1, and then divide it by the constant heat of vaporization. That is, mass of the water that you need to drink, all right, for replenishment. It is equal to the mass of the man multiplied by his specific heat and his change in temperature, divided by the constant heat of vaporization of water from the skin at normal body temperature. All right, and plugging in the data given in the problem to this working formula, we have 70.0 kilogram, that's the mass of the man, his specific heat, which is 3,480 joules per kilogram Kelvin, and his delta T, or change in temperature, which is 1.00 Celsius degree, or just the same as 1.00 Kelvin, to be divided by LV, right? The heat of vaporization of water from the body at normal body temperature. Okay, it is equal to 2.42 times 10 to the 6 joules per kilogram. And simplifying, we will get the value of the mass of the sweat that evaporates, or the amount of water that you have to drink for replenishment, equal to 0.100 kilogram, or exactly 100 grams. And moving on to question letter B, what is the volume of this mass of water? So we just use the formula for finding the volume, which is mass divided by the density. All right? So the mass is 100 grams divided by the density of water, which is 1.00 gram per centimeter cube. All right? We will get the amount of water, or the volume of the water that you need to drink for replenishment, equal to 100 centimeter cube. Now, when compared to the volume of an ordinary soft drink can, which is 335 centimeter cube, we say that this amount of water, all right, is much less, okay, compared to the amount of soft drink that you might consume, all right, if you're going to choose soft drink as your what we call to cool yourself, okay. Some people, they prefer soft drink than pure water, but of course we know that it's not really advisable, all right, to drink soft drink in place of water for replenishment, okay, after having perspired an amount of water, okay, that evaporates from your body, equal to 100 grams, or 100 centimeter cube, okay. Water is a better replenishment compared to soft drink, which we know is full of calories and glucose. All right. For question number 2, one suggested treatment for a person who has suffered a stroke is immersion in an ice water bath at 0 degrees Celsius to lower the body temperature, which prevents damage to the brain. In one set of tests, patients were cooled until their internal temperature reached 32.0 degrees Celsius. To treat a 70.0 kilogram patient, what is the minimum amount of ice at 0 degrees Celsius that you need in the bath so that its temperature remains at 0 degrees Celsius? Okay? The specific heat of the human body is 3,480 joules per kilogram Celsius degree, and that normal body temperature is 37.0 degrees Celsius. We'll have the solution to this question in a short while. For our solution, we will let Q1 be the amount of heat liberated by the patient to cool his body by 5.00 Celsius degree from the normal body temperature of 37.0 degrees Celsius just to be brought down to 32.0 degrees Celsius. So the delta T must be 5.00 Celsius degree. And then Q2, we let Q2 be the heat absorbed by the ice to melt and still remain at 0 degrees Celsius. So, this amount of heat liberated by the patient, Q1, is equal to the mass of the patient multiplied by his specific heat and his change in temperature delta T. While Q2, the heat absorbed by the ice to melt and still remain at 0 degrees Celsius. We just use the formula Q2 is equal to mass of the ice, alright, our target variable, and the constant known as heat of fusion of ice. Notice that there is no delta T because during the process of phase change, the temperature doesn't change. Alright? So, these two, Q1 and Q2, are supposed to be equal. Alright? And just like in the previous problem, when we are looking for Mi, the mass of the ice, alright, we just isolate, then come up with the working equation for Mi, mass of ice, equal to, alright, the formula for Q1, mass of the patient multiplied his specific heat by delta T divided by the constant heat of fusion, right? Where the delta T, of course, reiterating that the delta T is just the difference between the normal body temperature, 37.0 degrees Celsius, and the desired temperature, which is 32.0 degrees Celsius, all right? And completing our substitution in this formula, all right, we have 70.0 kilogram, the mass of the patient, multiplied by the specific heat, 3,480 joules per kilogram Celsius degree, times this delta T of 5.00 Celsius degree, then all over the heat of fusion for water, which is 3.34 raised to the 5th power joules per kilogram. And simplifying, we get the mass of the ice, okay, equal to 3.65 kilograms. So this is the amount of ice that has to be placed in the tub in order for the patient, no, to be able to what we call cool down, okay, from his normal body temperature of 37 degrees Celsius to the desired temperature, which is 32 degrees Celsius, right? A mass of 3.65 kilogram of ice, okay, of course this is understood mixed in water whose temperature is already initially at 0 degrees Celsius. So whatever amount of heat that is released, right, or liberated by the patient, we label it as Q1, right? All this amount of heat goes into melting this amount of ice, all right? Assuming that there is no heat exchange with the surrounding, including the water, all right, in the tub. Question number 3. You cool a 100.0 gram slug of red hot iron whose temperature initially is 745 degrees Celsius by dropping it into an insulated cup of negligible mass containing 85.0 grams of water at an initial temperature of 25.0 degrees Celsius, assuming no heat exchange with the surroundings. Letter A. What is the final temperature of the water? And question letter B. What is the final mass of the iron and the remaining water? Use specific heat for iron equal to 0.451 joules per gram Celsius degree and specific heat of water equal to 4.184 joules per gram Celsius degree. The heat of vaporization of water at 100 degrees Celsius, which is 2,260 joules per gram. So, for our solution, we first let Q1 be the amount of heat lost by iron to cool it to 100 degrees Celsius. So in this problem, we are talking about the amount of heat that is liberated, okay, by the hotter body, which is the piece of iron, and this amount of heat lost by the iron when it is added, okay, to the what you call uh, amount or water, okay, the same amount of heat lost by the iron is absorbed by the water, all right? And this is in accordance with the law of conservation of energy. Heat loss equals heat gain. Our assumption is that no heat exchange with the surrounding, okay, is considered in this situation, right? Amount of heat absorbed or lost to the surrounding will be considered negligible. All right, so how do we determine this Q1? We just use the formula for Q1 equals mass of the piece of iron multiplied by its specific heat and its change in temperature. Now, the delta T will be the temperature of the iron, okay, from its initial of 745 degrees Celsius to 100 degrees Celsius, right? We use 100 degrees Celsius because that is what we predict. Okay, we are predicting here that the equilibrium temperature of the system is going to be 100 degrees Celsius. All right? So, doing our math, when we multiply 100 grams by the specific heat of iron, 0.451 joule per gram Celsius degree, and the change in temperature from 745 degrees Celsius to 100 degrees Celsius, that's a delta T of 645 Celsius degree. And we will get the value for Q1 equals 29,090 joules. The amount of heat that will be absorbed by water is denoted here by Q2. All right. Just like in the case of iron, we will be using the formula for finding the amount of heat Q2. Just multiply the mass of the water, its specific heat, and its change in temperature. All right. So this is how we substitute the mass of water, which is 85.0 grams, its specific heat, 4.184 joules per gram Celsius. And the delta T will be the change in temperature from its initial of 25 degrees Celsius to the final temperature, which is 100 degrees Celsius. So that's a delta T of 75 Celsius degree. And simplifying, we get this amount of Q2, 26,673 joules. All right. So you must have noticed already that the two amounts of heat, Q2 and Q1, all right, are not equal. There is a difference between the amount of heat that is given off by the piece of iron after dropping its temperature from that high temperature to 100 degrees Celsius, all right, as compared to the amount of heat that is needed to raise the temperature of water from 25 degrees Celsius to 100 degrees Celsius. So Q2 is only 26,673 joules, whereas Q1, we calculated Q1 as 29,090 joules. So the difference between the two, which we label here as Q3, right? This is the amount of heat that is not what we call used, right? This is not used by water, okay, for raising the temperature of water from 25 degrees Celsius to 100 degrees Celsius. What does this mean? This simply means that there is a certain amount of water that has already, or that is going to vaporize, all right, because there is an excess amount of heat from the amount of heat that is released by the piece of iron, okay, which amounts to 2,417 joules. So this is the amount of heat that's available, all right, for a certain amount of water, all right, to vaporize. All right, so that is our next target. We will calculate for that mass of the water that will vaporize given this amount of heat that was released by iron. So we simply divide Q3 by the constant. This time it's called the heat of vaporization for water at 100 degrees Celsius. In other words, all right, Q3, which is 2,417 joules, when divided by this heat of vaporization equal to 2,260 joules per gram, then this is the amount of water that is going to vaporize. In other words, that will turn into steam, 1.07 grams. All right? So, in short, not all the amount of water that boils, okay, will be turned into steam. There is a certain amount of boiling water that remains, right? And that is just, of course, the difference between its original mass, 85.0 grams, minus the amount of water that has vaporized or turned into steam, 1.0 gram. All right, so The amount of boiling water remaining, of course, is 83.9 grams. So this amount of water is boiling at 100 degrees Celsius, so that our final answer to the question, the mass of iron, of course, hasn't changed, right? Whatever is the amount of iron initially, that will remain as is, all right? 100.0 grams. And the amount of boiling water remaining is 83.9 grams. These two, all right, constitute what we call the system that has reached what we call thermal equilibrium. Okay, the two are in thermal equilibrium. In other words, they have reached a final temperature which is 100 degrees Celsius. All right, and at thermal equilibrium, there will be no more exchange of energy or heat that will occur because the two bodies are now of the same final temperature. All right, this is now our last question, question number 4. As a physicist, you put heat into a 500.0 gram solid sample at a rate of 10.0 kilojoules per minute while recording its temperature as a function of time. You plot your data as shown in the figure. Question letter A, what is the latent heat of fusion for this solid? Question letter B, what are the specific heats of the liquid and solid states of this material? So you have here the graph, temperature along the y-axis in degrees Celsius, and the time elapsed in minutes. All right, you have here the graph line starting from, uh, what is this? At 0 time or 0 minute, all right, we start at negative 5 degrees Celsius. All right, so that point here corresponds to negative 5 degrees Celsius. And then, after 1 minute, all right, represented by this straight graph line, after 1 minute, the temperature of the body is now 10 degrees Celsius. And then, after 1.5 minutes, all right, from this point to that point, we have a horizontal graph line which suggests that the temperature doesn't change, right, within this time interval from 1 to 2.5 minutes. And then from 2.5 minutes up to 4 minutes, there is again an increase in the temperature, all right, a constant increase in the temperature until that temperature of 40 degrees Celsius. All right. So in other words, our graph is divided into 3 segments. Okay. The first one, sloping upward to the right, straight graph line. The second segment is horizontal. And the third segment also sloping upward, straight line graph, sloping upward to the right. All right. So answering the first question, what is the latent heat of fusion for this solid? So, our formula for finding the latent heat of fusion is simply to divide the amount of heat, all right, Q, by the corresponding amount of mass of the material. All right. So, latent heat of fusion, by definition, means the amount of heat needed, all right, to melt, okay, a given mass of the substance, right? Or reversibly, it can also mean the amount of heat released, right, by a given mass in order for it to what we call turn into solid, just like in the case of ice, right? When liquid water turns into ice, the amount of heat that it has to give off, okay, is what we call the latent heat of fusion. So how do we determine that? All right, we base it on the first graph line. All right, from negative 5 degrees Celsius to 10 degrees Celsius, okay, we say that uh, the temperature is increasing. So that doesn't suggest uh, a phase change. All right, that doesn't suggest a phase change for this substance because there is still a continuous increase in temperature. But in the second graph, which is horizontal, this suggests that, all right, as time passes, the temperature remains constant. So this suggests that there is a phase change going on. And this is what we are going to use as our basis for finding the amount of heat Q. All right. Notice that from 1 minute to 2.5 minutes, okay, which according to the problem, 10.0 kilojoules per minute, all right, is the amount of heat that is absorbed by the material in order for it to undergo phase change. All right. So 1.5 minute, that means a total of 10 kilojoules plus 5.0 kilojoules for a total of 15 kilojoules of heat is absorbed. All right. And the amount of the material or the solid sample is 500.0 grams. So dividing this amount of Q by the amount of mass, we will get the latent heat of fusion for this solid sample, LF equals 30.0 joules per gram. Okay, this is our answer to letter A. Moving on to question letter B. What are the specific heats of the liquid and the solid states of this material? All right. So if the melting point of this material is understood now to be at 10 degrees Celsius, all right? This is where the body undergoes what we call melting or the phase change that is from solid to liquid. In other words, at temperature below 10 degrees Celsius, we say that that the material is still in its solid state. All right. But when it absorbs heat, all right, there is a change, an increase in temperature. And that is exactly what we are going to use to determine the specific heat of the solid state of this material. Right? We do that by simply dividing the amount of heat that is absorbed within the time interval. All right? Obviously, the time interval is from 0 to 1 minute. So that corresponds to an amount of heat absorbed that is 10.0 kilojoules in the first 1 minute. So our value for Q is 10.0 kilojoules. All right. The same amount of the solid material, 500.0 gram, but the delta T is from negative 5 up to 10 degrees Celsius. So that that is equivalent to what? 10 minus negative 5. All right. That means a total of 15 Celsius degree temperature difference. Completing our substitution, we have here 10.0 kilojoules for Q. The mass is 500.0 gram, and the delta T is 15 Celsius degree. In doing our math, we will get the value for the specific heat. All right, the specific heat of the solid material, or the solid state of the material, which is equal to 1.33 joules per gram Celsius degree. Okay, and moving on now to the other question, what about the specific heat of the liquid state? All right, for the liquid state, we use the same formula, Q divided by M delta T. But this time, all right, we're looking at the third graph line. So the third graph line suggests that from 10 degrees Celsius to 40 degrees Celsius, all right, this material is already in its liquid form. All right. So how much heat has been absorbed? All right. That corresponds to a time of 1.5 minutes. All right. From 2.5 minutes to 4 minutes. That's equivalent to 1.5 minutes. And 1.5 minutes corresponds to 15. All right. 15 0.0 kilojoules of heat absorbed. All right, and the change in temperature, of course, is from 10 to 40, so that's an interval of 30 Celsius degree. Completing our substitution, here it goes. 15.0 kilojoules is the amount of heat divided by the same mass of 500.0 grams, and the delta T is 30.0 Celsius degree. And simplifying, we get the value for the specific heat of the liquid state of the material equal to 1.00 joules per gram Celsius degree. All right? So these are our answers to question number 4. For letter A, the heat of fusion of this material, LF, is equal to 30.0 joules per gram. All right. And for the specific heat of the solid state of the material, we got 1.33 joules per gram Celsius degree. And finally, for the specific heat of the liquid state of the material, we have 1.00 joules per gram Celsius degree. So that's it. We are done with our video tutorial. Thank you very much, as usual, for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.